Okay, so in a nutshell, this is how we examine or this is how we analyze the performance of algorithms. And these define certain classes of algorithms. As I have said earlier, if it has a polynomial or better runtime, we actually treat that as a good algorithm in terms of runtime complexity. Otherwise, it's not preferable. So, some terminology here. Problems for which a solution can be found in polynomial time constitute class P. This obviously involves a polynomial time or better. And this we call algorithms class P. So P stands for polynomial time. Problems for which a candidate solution, which you do not know whether a solution or not, but you are given a candidate, okay, this might be a solution to your problem. Uh, Problems for which a candidate can be checked or verified in polynomial time constitute class NP. Okay, so this is a little bit different than class P. Here, we are not talking about finding the candidate, but we are given a candidate, right? And we can check whether the candidate is really a solution or not in polynomial time. If that is the case, we call these problems class NP. Now, by the Church-Turing thesis, any function whose values can be computed by an algorithm can be computed by a Turing machine. Okay, I'm not going to go into the details of this, but sometimes this is taken as a definition rather than a hypothesis. So this means that Turing machines again play a central role in the analysis of algorithms. So our definitions, again, in a formal sense, our definitions are based on Turing machines. A decision problem that can be solved using a deterministic Turing machine in polynomial time in terms of the size of its input is in class P. This is the formal definition. If you have a problem, a decision problem mainly, and that exists a deterministic Turing machine, this is important, deterministic Turing machine, that solves this decision problem in polynomial time where the variable of the polynomial is the size of the input. Okay, if that is the case, that problem is in class P. On the other hand, a decision problem that can be solved using a non-deterministic Turing machine. Now, this is the key difference here. Non-deterministic Turing machine in polynomial time, again, in terms of the size of its input, is in class NP. Okay, the class NP, maybe you have seen these concepts earlier, but let me emphasize, many people mistake the class NP to be the class where you have non-polynomial solution time. That is incorrect, okay? NP do not stand for non-polynomial. That's not the case because, well, if you look at the definition, class P must be a subset of NP because for any problem that you can find a solution in polynomial time, you can obviously check any solution, any candidate solution in polynomial time too, because you can come up with the solution and check whether the given candidate is among the solutions or not. Rather, it's not non-polynomial, but the name NP comes from non-deterministic polynomial. Okay, now remember how a Turing machine works. You have the finite automaton and you have the tape. And you have the quintuples that describes what action to be taken at each slot. You have the current state and the current tape symbol. And based on these two, you have the next state and the symbol to be written on tape and the direction. Now remember the distinction between deterministic Turing machines and non-deterministic ones. In a deterministic Turing machine, the pair current state and current tape symbol gives you a unique action to take, or maybe not. If that is the case, the machine halts. But if there is a rule, that rule is unique. So if you have the current state and the tape symbol, what you need to do is deterministically null. On the other hand, with a non-deterministic Turing machine, there might be multiple rules to be done when you have the current state and the current tape symbol. So all of those lead to execution branching. And by using that, you can actually check a candidate solution, whether that is a solution or not. You can check it using a non-deterministic Turing machine by actually branching out for every possible input. Okay, so that's how you can actually determine or you can verify or check a candidate solution using a non-deterministic Turing machine. Now, obviously, all deterministic Turing machines are special case of non-deterministic Turing machines, which also tells us that P is a subset of NP. Okay? But you have to understand what the class NP entails. Okay, class P, that's straightforward. You can solve a problem in polynomial time, that's in class P. But what is NP? NP is, well, these are two equivalent definitions. One definition is you can check a given solution holds in polynomial time. Look, you are not finding the solution. You are just checking a given candidate in polynomial time. Or, with respect to Turing machines, you can find a solution. You can actually find a solution using non-deterministic Turing machines. Okay, how can you do that? You branch from your current state with respect to every possible input, and since they are going to execute in parallel, and at least one of them will lead you to an accepting state if that candidate given to you is a solution, then using a non-deterministic Turing machine, you can actually find a solution. So these are two equivalent definitions of class NP. Now, problems in class P, we call tractable. Okay, so they are good to be executed, good to be implemented. They are well behaved. You can implement them usually in any type of computer without any serious problems. Whereas problems not in class P are called intractable. So these are typically the problems with exponential or factorial runtime, so that beyond a certain limit, it will not be really feasible to execute on a computer.